in NUCLEON experiment, we investigate so-called near region. Near region was discovered approximately 50 years ago in Soviet Union. Christiansen and Kulikov found that spectrum of cosmic ray go sharply decreased, but in area was about 10 to 15 electron volt. This inclination is changed, and it was many long discussion. What is the reason for this knee? It may be some effect of interaction, high energy interaction. For example, if at the energy you reach the threshold for creation some heavy particle like a muon, and in shower at the energy 10 to 15 arises muon, which give small signal on in the detector, because we investigate the extensive air shower, and contribution of heavy muon, which take 20 or 30% of energy, but it is not really change property of shower. But according to investigation property of shower, you can evaluate what is the energy of initial particle, what is nature of this initial particle. But now, but also another reason, it was completely different. It is connected with property of our galaxy. Our galaxy has definite size, definite magnetic field, and at the energy about 10 to 15, value of our galactic and value of magnetic field not efficient to keep charged particle inside. And charged particle with energy more than 10 to 15 more easy go away from our galaxy. And so we see it as change in cosmic ray flux. But now, as you know, start working LHC accelerator at CERN, and 10 to 15, it is energy was before LHC, it is the more powerful accelerator. It was Fermilab. Fermilab is just at its energy before 10 to 15. But if we speaking about LHC, it is fixed target energy correspond 10 to 17. So this region we go through, and if it reason was some new phenomena in nuclear interaction, we already found something, but nothing was found like heavy muon in LHC experiment. So this is a hypothesis connected with high energy physics, now is killed. And only the possible explanation is some galactic phenomena. And 10 to the 15 energy, it is a natural value which arises if we are thinking about mechanism of acceleration of charged particle. The standard model of acceleration cosmic ray, it is supernova explosion. During the supernova explosion, arises a shock wave, and in the front of shock waves, just arising a condition for acceleration of charged particle. And it is natural, there exists some limited value which possible to accelerate with this mechanism. And just around 10 to the 15. Работает или нет? Doesn't work. Okay. And according to this model, this knee it is different. During the acceleration, accelerate all the nuclei which exist during the explosion of supernova, from hadron and more heavier nuclei that arise during the thermonuclear reaction in star. It is iron. Iron, it is more stable nuclei, and it is natural to investigate and see some changing of cosmic ray composition around 10 to the 15. This knee is different, has a different location for proton and for iron nuclei. And this is aim of our NUCLEON experiment: investigate cosmic ray spectrum around knee, and we will measure very well charge of particle, initial particle, and try to clarify this question. Okay. Next one. So now I describe this situation with NUCLEON. With TUS experiment, the situation quite different. Region where we are working with TUS, it is 10 to 20, not to 15, 10 to 20 electron volt. Next one. This is cosmic ray spectrum. You see, multiplied to energy to the 2.7 value to see more clearly the situation. It is NUCLEON region, it is knee region, and this is region for TUS. For TUS, problem connected with microwave background. At energy 4 times 10 to 19, it is threshold value where cosmic ray proton with such energy begin to interact very strongly with background photons. With energy in each interaction arises so-called isobara resonance, and obtain during this interaction charge of energy go to pion, which rises during decay of isobara. In each such interaction, approximately 20% of initial energy it go away. So it is a free path in in space. You know that density of microwave photon it is about 400 cubic centimeters, and if you calculate what is free path of high energy proton, such energy it is about 50 megaparsec. So this phenomenon was predicted immediately after microwave radiation discovery. It is approximately 50 years ago. And so, in principle, if we in our study found particle which has energy more than 10 to the 20 or more than 4 times 10 to 19, it means that this particle, source of this particle, not too far out of us, because it has to be nearer than 50 megaparsec. So, in such a way, value of magnetic field not enough to change direction of this proton, and with such high energy, it's possible to do proton astronomy. You can see source of this proton with such energy. But situation it is not a clear result of different experiments, very different. What was obtained in the last year, shortly before 10 years ago, it was in a gas experiment, which was working very hardly in this. They found no such cutoff. This is GZK cutoff, Grazen-Kuzmin-Zatsepin cutoff, which was predicted 50 years ago. They found no such cutoff, and this is very unusual, very excited phenomenon. And since this time was a few experiments after Agasa, HIRES-1, HIRES-2, AG, now a telescope array, and now what we have considered that such a GZK cutoff exists. But a problem what is not decided, where is the sources of this cosmic rays, and what is composition of this. Next. This is a result which presented recently in AG collaboration at this region, the 10 to 19 to the 20. And you see, it is just GZK cutoff. Before this, Agasa, people point will be was in this region. Next one, please. This is comparison to two more powerful experiments which are working now, ground-based experiment. Telescope array in USA and AG detector in Argentina. And you see the result is rather different, and it is seen more clearly on the next slide. If you see here, it is the result of different experiments, including Akena Agasa, this HIRES, AG, etc. Difference of this in cosmic ray flux is measured very differently, not coincide. But if you include the systematic errors with measuring of flux of this is shown different contribution. In principle, possible to move all this data of different experiments and obtain such a behavior. What is here? Here it is just GZK, but it is some theoretical trick to play with data of experiment. It is not very conclusive in such a way. This is reason why we try to work in this area with space experiment. Situation with detector in space is rather different in comparison with ground-based experiment, because in this experiment we will measure flux of fluorescent photons. Fluorescent photons arise in extensive air shower because part of energy of shower go to excitation on air nuclei, and fluorescent photon go isotropically in different direction. And if your detector is on the ground, that for photons which go from the shell to your detector, they go in more unstable, more heavy, more unpredictable atmospheric effects. Because in lower part of atmosphere, this is effect more powerful. If your detector in the space, condition is more stable. So also this different of result of different experiment also may be connected that different experiment looking on the different part of sky. And in principle, if we are talking about proton astronomy, maybe proton astronomy in the south part of sky and in the north is different sources. But if your detector is on the space, we're looking everywhere. And this effect will be also maybe investigated. Next one. And what is also discrepancy between these two experiments, it is what is initial particle, proton or iron. As I say, proton is naturally because after end of all thermonuclear reaction in star, we have rather reasonable number of proton, but also a reasonable number of iron. But it is necessary to distinguish. Here, what is it is this development shower in atmosphere. It is depth in gram per centimeter square. Your shower go up to maximum and then it go down. It is simulation for proton. It is simulation for iron. You see that fluctuation in proton naturally more because in iron nuclei you have 56 nucleon, and all the shower some average effect. So some fluctuation is much more narrow. X mass position depends on energy. It is shown for initial proton. It is for nuclei. You see, this is E divided by I. It is energy of one nucleon. Next, please. See here comparison these two data, AG data and high-res data. High-res, it is previous experiment before telescope array. Telescope array, it is next step of high-res. And here it is energy, logarithm energy. Here it is X max value. You see the remarkable difference between two. In more clear, this difference is in this fluctuation. In fluctuation, and according to AG detector, this energy 10 to the 15, we have to see iron, mainly iron. Not so this for telescope array or high-res. They predict the proton. Next, please. And this picture, it is connected with sources. Here it is part of our galaxy, and this blue spot, it is so-called active galaxy nuclei. Active galaxy nuclei, it is one of more popular source of particle of ultra high energy array. Black point, it is data. And if you try to find correlation, if it exists correlation between active galactic nuclei and angular arrival direction for your data. Only it was selected more high energy particle. And in a G detector, they at the beginning they more strongly was statement they have found correlation. Now it is not so, because statistic was increased, but correlation was decreased. High-res, no, at the beginning and up to now has no such correlation. But nevertheless, if you nearest take one of the nearest galaxy, active galactic galaxy Centaur A, what is shown, and see what should be distributed, your position of angular distribution difference of your event in comparison position of Centaur A. There is some irregularity. And people of AG detector said that maybe it is some indication that this galaxy, it is source, one of the source of this this event. Next, please. So, open question, it is where is correlation? What is composition? What is composition iron nuclei? Also, where is gamma? Because during this interaction with background photon, you obtain pi0 meson, which is decay into gamma, and in principle, it's possible also to find gamma in the same energy region. No gamma was found up to now. Yes, please. Shortly about nucleon. Next, please. I said this is what Christiansen and Kulikov. It is the original discovery of Ni. Situation with Ni is presented here. Presently, it looks like here. It is logarithm atomic number. If it was only proton, you have logarithm of unity. It is 0. You see that with increasing of energy, your composition is more heavy nuclei inside of. Next, please. So, no, it is more or less, let's say, it is a lot of experiments, which all of them very clear see this Ni. But according to models, to models of acceleration, Ni is different. For proton, Ni it has to be around 10 to 15, but for iron, according to this model, is 10 to the 17. 10 to the 17, it is unreachable, unfortunately, area for nucleon, because flux is so small that in detector like nucleon, it's impossible to measure. Next, please. It is a phenomenon which also found in last, I think, 3 or 4 years. What found anisotropy of cosmic ray. Up to this year, was tried to find anisotropy. No conclusive result was obtained. But now, what result we obtained here? To find this signal, it was necessary to get huge statistics. This data, it is Milagro detector, iScope detector in South Pole. It is in United States detectors, which measured extensive air shower. They have approximately 10 to 10 events, 10 milliard events to find this picture. You see different colors show intensity of radiation. No, difficult to say that there is some correlation between north sky and south sky. But this is shown nearest pulsars, because pulsar, as I say, it is young pulsar, which arises just after supernova explosion. So it is possible source of all the cosmic rays which we investigate. But this clear contradiction, because energy of this particle is 10 to 20 TeV, 100 TeV for this experiment, and if you measure gyromagnetic radius, it is 0.1 parsec. But the distance for this pulsar about 100 parsec. So particle has completely forgotten what is the source of where they exist. It is necessary approximately 1 million years between creation particle and detection particle. With such a gyromagnetic radius, completely forgotten of the source. Next, please. So composition, it is a question. What is, as I show, charge of particle and anisotropy. Next. About the more detail in the nucleon experiment. It consists charge measuring system. It is silicon pad detector. Then there's some target. I should explain what is why we need the target. This detector is direct study of cosmic ray. There are two possibilities. Direct study, it is on the satellite, on the balloon, and indirect investigation, extensive air shower. The difference is clear. We, with our charge measurement, directly measure charge of initial particle. To find what is initial particle in the investigation, extensive air shower, it is very difficult problem connected with simulation. And so people try to go as possible to with direct measurement, but flux is decreasing, and for such a detector, it is impossible to go too far to measure directly. So it is after target we have some tracker, and at the below, at the bottom, it is some microcalorimeter. Next, please. Together only 10,000 channels. What is the investigation? With all the weight of this detector, only 300 kilo. But for good measurement of energy, we need calorimeter. And for calorimeter, we need not 300 kilo, but a few tons of detector to calorimeter. But this experiment was proposed when it was impossible to obtain a rocket which launched heavy detector. Not in Grigorov time, it is during the 16th. So initial particle in target, it is vertex of the first interaction, and in tracker we are measuring the tracks of all charged particle which in initial in the primary vertex, and all the gamma all the electron positron pair which arise during conversation of gamma in tungsten converter. So we measure all the secondary tracking of secondary particle. And if we propose, so transversal momentum of each particle is about 300 MeV, as is found experimentally, we can evaluate energy of initial particle. And accuracy is not very well, about 70 or 80%, but for cosmic ray point of view, it is not so bad. But we measure very good charge. There we have 4 layers of silicon pad detector, and it measures very well. I'll show you the result of test. Next, please. It is the same drone, which is from our technical design report. No, I explain, we measure number of secondary particle and pseudo-rapidity. It is connected to the angle of, in comparison direction of initial particle. Here comparison, dependence of energy before converter, and after converter, on the charged particle, this is all particle. You see that dependence on energy is remarkable, and this shown by this formula, and this principle used to measure energy. Next. Dubna was responsible for production of So I forgotten to say that Dubna was responsible for production trigger system, because to investigate only high energy part of the spectrum, we need trigger system. Trigger system was made in Dubna. It is 6 layer, 3 modules. You see, this is 3 modules of trigger system. Each module consists of 2 planes, silicon strips, scintillator strips, in perpendicular direction, and from one side of S3 you see on all the plane by 1 channel multiply, you obtain signal from all the plane. From other side you see signal from each strip. And this signal from 1 channel PMT used for trigger of first level only on energy. But if you have know where is strip is given your answer, you can roughly find the direction of this shower. This is for trigger of second level. 3 layer. 6 planes. It is many times duplicate system because it's very important. If trigger system will be doesn't work properly, all the detector is unusual. Next, please. So it is our trigger system during test. It was space qualification test very strongly because it is not the automatic apparat, and acceleration will be huge, and so overweight and vibration was very small. It was tested in special apparatus. Next. It is our electronic, it shows the duplication, etc. Next. It is an example of charge measurement system. Only one ladder. For one side the detector, on another side is all the electronic. Next. It is completed one of plane, this charge measurement system. Next. It is tracker. It consists of microstrip silicon detector, thickness of 300 micron, and width about 45 micron. Next. It is our calorimeter. Calorimeter is aim of this calorimeter is double. Part of event will be measured in calorimeter, but and the same event will be measured by kinematically method which I described you before. And another part of event will be measured only kinematically, but you can calibrate in the flight comparison with 2 different methods. It is our technological model of our detector prepared for tests. Next. Here it is test facility to test all the detector, not on the trigger system, but all the detectors. Next. Here flight model of our detector during the last test at the beam, because we tested this apparatus many times and the different beams. Next, please. Next. So you see it is shown only qualitatively explained. It is efficiency of trigger system. You see, if in possible trigger system, aim of trigger system is to suppress unusual event at the level 10 to -5. And you see that already in the first test, which was done a few years ago, we easily obtained 10 to a few about this value. But now 10 to the 5, it is good value which was obtained in other. Here it is also beam result test, how we see the beam with trigger system. on the next time, the same beam as it was measured by our tracker. It is completely correspond what is the profile of the beam, really beam. Next, please. It's an angular distribution. Not the distribution, it's our angular resolution. Because angular resolution it is important if we will try to investigate anisotropy. You see it is around 1 degree. Okay, it is some illustration of our charge resolution. It is noise. It is proton. That during this day that we have only we are working on the proton beam. In this February we are working with nuclear beam, and you see charge system gives very good resolution, charge resolution. It is just our 4-layer of our charge measurement system. Here we have tested new chip. New chip was developed for next for our calorimeter, and you see that this charge resolution is even better. But there are some technical detail. I don't describe it. Next one. It is also distribution of the beam with our calorimeter. Next, please. It is about energy resolution. It is we are working with iron beam with this energy per nuclear, and this is our result of our measurement. And if we investigate the value of energy according to our measurement, the difference is reasonable. 158. Here is 154. Next. So about our apparatus, it is now we are prepared. The detector is completely ready. The complex test nearly a month will be finished. Here our space platform, which will be used. You show some parameters. Please next. And this is some example. Example after only 3 years of data taken for Proton. It is data which exists now in this region, and what is expected after 3 years of working in the space NUCLEON. Our future, a few words about future. Next. As I say, NUCLEON detector has approximately 10,000 of channels, and we have only 15 watt of energy, limited possibility for data transmission, and naturally, it was people who participate in preparation experiment obtained a proposal to prepare a project of next step experiment. One of possibility is used for nuclear energy source. Here it will be nuclear energy source. This will be our experiment. It is for different system of our detector, different chamber, etc. Different here that we have about 1 million channels. Weight here it is shown only about 3 tons, but now it was discussed 3 or 4 years ago. Now talking about detector weight of 7 or 8 tons, much more powerful. One of idea to develop 3D calorimeter. Very difficult task. Up to now, was no prototype of that detector. We tried to do it, but we have also some another proposal. Next, please. It is some picture how it looks like. Next, please. This is some simulation for electron, for proton, 20 GeV. You see the huge of tracks. Next, please. Also, you see that possible selection between electron and proton events. Next, please. And one also idea of this experiment to measure not only charge component in shower, but also neutron component. It is a rather long story to tell you how we try to do, but in principle that's possible. It is charge signal of charge particle. It is neutron signal. It is delayed in time. Distribution rather not sharp, difficult to investigate, but number of nucleon, neutron in initial electron particle or proton particle differ in 100. So it is interesting to select initial particle. Next. This is another possibility which we propose to do. When you have not the cubic but calorimeter on such a way, where strips go in different directions, x, y, u, v direction. You saw quasi 3D calorimeter, and we tried to use this. We have made such a prototype and tried to investigate if we can provide tracking in such calorimeter, if we can see if we can find the neutron signal. But unfortunately, tracking is possible. Neutron signal is with such small detector impossible. As we found in simulation. Next, please. So I near to a conclusion. Technological model of nucleon is now at the final complex text in Arsenal Space Center in St. Petersburg. Flight model is preparing for test together with space platform in Samara Progress Space Center. And probably at the end of this year, beginning next year, we start data taking. Все, ну-ка еще там что у меня есть. No, also our next detector, which is maybe will possible to go to 10 to 16 EV. It is after NI. That's all. Let's see. Please.
Is data taken in real time, or how much is the time resolution?
Loudly, please.
The data is taken in real time, or how much will be the time resolution, or the time elapsed between cosmic ray hit the detector, and then you
If you're asking about nucleon experiment, of course, data will be automatically obtained and written, and it was some on-board filter. But for offline analysis, connection between our detector in orbit and our ground station, it was limited number of ground stations to get data, and probably during the 24 hours we will obtain only 2, 3, or 4 possibility to get all our data and investigate it on offline. About time resolution. Time resolution is trigger system give time resolution about 10 or 20 nanoseconds. But if you obtain trigger, and then to transmit all your data from the detector to memory, it's necessary a few microseconds. So our trigger rate will be, I think, 100 per minute, something like this. But it is not so good because, not so bad, because flux in this region not that huge. The more interesting event is go not more quickly.
Given the symmetry of the detector, I mean you have only one axis, do you plan or do you have a way to direct the detector to some cosmological sources just to...
Detector will fix it on the space platform hardly. So orientation of the detector mainly connected with solar panels to obtain power. But from the physical point of view, your flux of your cosmic ray more or less isotropic. Anisotropy, it is about 0.1%. So it is not so important if you look in this direction. But in simulation, of course, we comparison how changes the property of our detector if it goes along the z-axis and what is real our acceptance value.
Well, it's more or less in the same sense. Which is the sky coverage information?
Sorry?
The sky coverage. Which is the percentage of the sky?
Percentage for nucleon, it is 100%. 100% because no limitation. For us, we are working completely day and night, and I think it's 100% coverage. 5 years.
What about this same situation?
Sorry.
What about TUS experiment?
TUS describe about TUS. About our TUS, what was done in Dubna, and what we expect with data taken. Probably here answer your question.
I have a question about the acceptance of TUS in comparison to the RESURS acceptance.
Oh, I think Artur answer also for you. Maybe continue with Artur, yes? Давай. Тебе помогать? Сам будешь? Так, вот. Это вот желтая кнопочка.
Subject of my course, ultra-high energy cosmic rays detector TUS. Recent results obtained at ground-based detectors, experimental arrays, do not give clear answers to the most important questions in the field of ultra-high energy cosmic rays physics. For example, mass composition and possible sources of the most energetic particles. Statistics beyond the GZK limit is still very low. The TUS space experiment is aimed to study energy spectrum and angular distribution of the ultra-high energy cosmic rays at the energies 10 to 20 eV. The main concept of TUS was developed in the beginning of this century as the first stage of larger detector wiev. This is a Russian abbreviation of ultra-high energy cosmic rays. Later, this TUS detector was modified for launching on board of various satellites, and recently is planned for launching on board Lomonosov satellite. The view of TUS detector on board Lomonosov satellites is shown on this picture. Detector TUS consists of following parts: mirror-concentrator, the main part, photoreceiver movement system, and solar light sensor. Fresnel-type mirror-concentrator focuses ultraviolet light generated by ES particle disk to photoreceiver, which consists of 2056 photomultiplier tubes and support electronics. Photoreceiver moving system changes position of receiver from transportation to operation mode. It is also capable to remove receiver out of mirror focus in case of danger from concentrated sunlight. Alarm signal for removing receiver comes from directional solar light sensor. Image of shower particle disk moves along photoreceiver pixels and produce sequence in time signals in one or more pixels. Event with many hit pixels is considered as inclined shower event. Data on space-time shower signal distribution give information on direction of primary particle, its energy, and position of shower maximum. The main parameters of the TUS detector is presented in this table. Mass is about 60 kilograms, power 65 volts, field of view plus minus 4.5 degrees, number of pixels in the photoreceiver 2056, pixel field of view, total area of the mirror about 2 square meters, focal distance 1.5 meter, duty cycle 30%. On this slide, we can see TUS photo detector. Photoreceiver comprises 2056 pixels combined in 16 clusters. 200, sorry. 256 pixels combined in 16 clusters. One cluster and wall photoreceiver are shown in the pictures at the right. Each pixel contains the photomultiplier tube of Hamamatsu type with glass window transparent to ultraviolet. In front of PMT, the filter is placed to separate radiation with wavelength range 200–400 nanometers from visual light. Signals from every PMT tube are coming to multiplexer and then to IDC. The fast signal from an ultra high energy cosmic rays event are collected every 0.8 microseconds. For increasing light collection efficiency, we use some light guide system. Light guides with square window of size 15 times 15 millimeters are used for having higher fill-in factor in pixel area. On these pictures, we can see a full set of light guides, 16 times 16, single light guide with conical inner surface, PMT pupil with light filter placed in this position. On this picture, we can see photons density distribution on the PMT pupil, the results of simulation with vertical beam, light beam. Last picture, on the last picture, we can see theta dependence of light collection efficiency In the red, this is light collection efficiency, and blue without any light guides. Efficiency without any light guides. It is shown that light collection efficiency is almost 100% for the TUS field of view.
What was on the x-axis?
What?
On the x.
Theta and efficiency.
Ah, okay.
From 1 to 42 persons without any guide. The mirror concentrator is shown on this picture. The mirror is divided into one central and 6 lateral hexagonal modules. Each module is designed as sum of the parabolic segments, 2 for central and 11 for lateral ones, focusing a parallel beam to single point, Fresnel lens. In this design, thickness of the mirror construction is small, approximately 3 centimeters, which is important for mirror implementation into satellite construction. Mirror focal distance is 1.5 meter, and total area is approximately 2 square meters. Mirror segments are made of carbon plastic strengthened by honeycomb aluminum plate, so that the mirror construction is stable in wide range of temperatures. On other pictures, we can see the flight mirror in the ISTRA Space Center in the Moscow region in Russia. The flight mirror assembled on the space platform and TUS detector in operation position. The mirror module prototypes were produced and tested in 2008-2009. The blank modules were covered by 120 nanometer layer of pure aluminum and 40 nanometer protective layer of magnesium fluorine 2. TUS mirror passed various space qualification tests, vibration tests on this picture, and thermovacuum tests. On this picture, we can see TUS module inside thermovacuum camera. The fiducial net reflection was used to check the mirror optical quality. In these measurements, no discrepancies in the mirror properties were found. Other performed tests also have shown a stability of the mirror optical quality in the space conditions. The optical parameter measurement was an important part of the TUS preparation program. Results of these measurements are very significant for future data analysis, and moreover, in these measurements, the best mirror modules are selected among all produced ones. The special procedure was elaborated to measure the mirror module optical parameters. The Eclipse, this Eclipse machine, coordinate measuring machine from Carl Zeiss, complemented by a screen, laser head, and web camera shown in figure were used for the point spread function measurements of the lateral and central TUS Fresnel mirror models. The mirror model was installed to be parallel to horizontal table of the measuring machine here. The screen was mounted parallel to mirror at some distance above. Measurements at different distances between mirror and screen were necessary to establish a mathematical three-dimensional model of the mirror. Homogeneous parallel light flux was simulated by moving the laser beam across a mirror along the prescribed trajectory controlled by PC. The laser beam was reflected from the mirror on the screen and has to be movable for ideal mirror. In case of ideal mirror, and the screen location at the focal plane. The angle between laser beam and machine table is changeable and was fixed in every run of measurements. The screen images of the laser beam spots were written online by the web camera to another PC with the fixed frequency frame rate. The speed of laser beam movement and the frequency frame rate were selected and fixed to get 3 millimeters distance between the neighboring measuring points on the mirror. So we perform the scan our modulus step by step across the surface. This is the idea. A special procedure was done to measure laser beam location on the mirror and its reflected image location on the screen. As a result of these measurements and their analysis, we have obtained one-to-one correspondence between beam location and reflected beam spot on the screen. Results of measurement at focal distance for one model obtained by inclined beam at different polar and azimuthal angles are presented in the right panel. Trajectory of the laser beam along mirror surface is presented at the left. Each point in every spot of these plots corresponds to a certain point on the mirror surface. Total amount of spots collected in each spot is about 25,000. Just a moment. We have carried out several measurements for each model at different mirror to screen distances and different angles between laser beam and optical axis direction. The main goal of the measurements was to get a geometrical mirror model that should fairly reproduce all data and can be used for an arbitrary beam direction simulation. It will be important for ES track image reconstruction to do these measurements with a vertical parallel beam were used. The results of what? Oops, sorry. The results of the spots point-by-point diagrams for central, for lateral, for a certain lateral model is obtained for beam parallel to optical axis and various mirror to screen distance presented with Y labels. The measurements we can see on the picture on the bottom picture. Using these measurements, we obtain geometrical mirror profile, so-called discrete three-dimensional mirror model. This model may be treated as a set of size approximately 10 to 5 points of unique point-like reflectors. The simulation with this model we can see on the picture on the top. The simulation results are in excellent agreement with all measurements. spot point by point diagrams for lateral model obtained at focal distance for inclined beams presented on these pictures. At the left we can see measurements, and the right simulations with discrete model. Nevertheless, for providing possibility to simulate an arbitrary beam, it is essential to approximate discrete model at full mirror surface areas. In this way, certain difficulties arise due to a huge number of parameters in a discrete model, is around 1 million, near 1 million. But they might be overcome in various ways. Our results of this approximation for full mirror, so-called continuous mirror model, are presented in these figures. The figures on the top is a discrete model, points on the mirror, two-dimensional distribution of the reflected spots on the screen for inclined beam with theta equals to 3 and phi equals 45, and this image in photo-like type. This is the same. And for continuous model, the spot center and its size is almost the same in a discrete and continuous model. Finally, we have compared PSF angular dependence for two models, ideal mirror model and continuous three-dimensional model constructed from data analysis. The results are presented in this figure: continuous mirror model at the right and ideal mirror model at the left. There is naturally almost no phi dependence due to small difference between lateral mirror models. Simultaneous absence of the phi dependence in a continuous model confirms correctness of procedure of the point spread function angular dependence evaluations. There is an obvious difference with the same angular dependence for the ideal mirror that is presented in this figure. Now, the simulation. Fast parametric shower simulation, generation on fluorescent and Cherenkov light, and propagation through the atmosphere, including reflection from the surface of the Earth, were done with user simulation and analysis framework package. This figure gives a favor of statistics generated by ISAF. 4 points along the shower are presented, entering points of the primary particles in the atmosphere filled by red, interaction point filled by CERN, maximum of the shower filled by blue, and imaginary impact point on the Earth. Now, using ISAF simulation package together with optical mirror model and taking into account light-guide system, we might calculate signals in the pixels produced by an arbitrary shower. The example of such simulation are presented on these pictures. The picture on this picture we can see a light intensity in photomultipliers. On the next picture we can see photon distributions in the pixels in persons, and distribution by signal appearance time on the last. Bottom pictures, on the bottom pictures we see the same, but for ideal mirror model. And obviously some difference presented. Mirror surface was determined. Mirror surface for a continuous mirror model was determined with reflection coefficients 0.85. Now, on this slide, I will present two trigger systems schematically. On this picture, we can see a shower cascade curve for proton with energy 10 to 20 eV. Time step for our in this experiment 0.8 microseconds. On this picture we can see amplitude distribution for all PMTs filled by black, and contribution of shower is filled by blue. This photomultipliers are shown on this picture, and this closed by blue ellipse. TUS will operate in variable night atmosphere background. The special trigger algorithm was developed for this experiment. First selection of shower events, two-level trigger is implemented. The first level of shower selection is done to every pixel as a signal above the threshold, here, on this picture. Separate shower selection is done for two cases. When at least 3 neighbor pixels are triggered in the first selection level during sequential time intervals, and 2, when signals in 1 pixel are larger than the first level threshold in 3 sequential time intervals. On the last picture we can see pure trigger efficiency, we see energy for different thresholds. This efficiency is near 1, 2. Okay, expected statistics. On this picture we can see expected statistics for TUS experiment is filled by blue points for different energies. My conclusions: Detector TUS is ready to integration at the satellite Lomonosov. It passed all pre-flight tests, and it will be first orbital ultra-high energy detector which will test this technique of measurements and give important information for future projects as GEM-use and CLAP. In 3 years of operation in space, TUS exposure will be 12,000 square kilometers per year per steradian. That is comparable with exposure of the largest ground-based detectors. Offline reconstruction program development is in progress. Thank you for your attention.